Okay, good morning. So let's start the morning session. The first speaker is Professor Haruzo Hida from UCLA. The title is Lectures on the Anticyclotomic Main Conjecture.
Thank you for introduction. And I'm happy to come back here. 3 years ago, 2022, I gave 4 lectures, almost 90 minutes. This time, I got old, so I begged not to give 4 lectures. Jack Tiroin helped me, and therefore, I give 2 lectures. So what I will do is that first, Jack Tiroin proved that, or at least explained that, this is a relative class number, the class number of the co-kernel of the natural map from class group of F into class group of M. M is a CM extension. So, but anyway, we assumed P is odd, so it is also up to unit HM over HF. But perhaps Jack used this notation. And that guy times the cat periodic where the anticyclotomic part with branch character chi, the anticyclotomic character, that divides congruence power series H. And this H is a kind of branch character of H is, so this branch character of this guy is chi, and this is written as a psi minus projection. That means psi 1 minus complex conjugation inside. And in this way, it is written, and the branch character is psi. Okay, and he proved this inside in lambda P inverted. The first purpose of this talk is to remove this bracket. It looks stupid. Jack proved for infinitely many primes. I proved this for 1 prime. And this is the hardest thing to do. And so that's, I don't actually prove, but I mean, 3 years ago, I gave here that long ago, 2004, I claimed that if you fix a L conductor, L is prime to P, Gaussic L, and suppose this Gaussic L is totally split in F, and then you take a class group of M of this Gaussic L to the infinity, and you pick a character, Hecke character, say phi into say W. Now, this is a width vectoring. That for Jack, it was our Galois group, but I use this W for the width vectoring of algebraic closure of FP. And for, so this is almost ZL cross, almost ZL if you write additively. And 2004, I claimed that the, except for finitely many these characters, Hecke L value for fixed L0 phi. So Hecke L value, you just fix L0 and 1 Hecke character lambda twisted by phi. And of course, you need to divide by canonical Néron period of CMR-William variety. And this is not congruent to 0 modulo maximal ideal of W. That I claim, except for finitely many such phi. And the people believed it. I gave a proof. And after about 14 years later, Akshay Venkatesh found an error of my proof. And so I recovered the proof, but I couldn't recover except for finitely many. I could recover only for Zariski densely populated. I don't define Zariski density for this case, but character, it is non-zero modulo maximal idea. And I used this fact to prove, to remove this in my 2006 paper, Documentamas. I call it anticyclotomic main conjecture. So I claim the proof of anticyclotomic main conjecture. And in this step, I used this fact for that. Therefore, it appears that my proof of this AMC paper is incomplete. Although in the paper with Jack, I should have said perhaps there's some diagram here, but perhaps it looks not so important. I just erase it. So the Jack's talk is basically Hida paper 93, Analysis scientifique école normale supérieure, and HT 94 Invenciones paper, he explained that stuff. And in this École normale supérieure paper, I at least said that if one could prove the vanishing of mu invariant of Katz periodic L, this you can remove this 1 over P. And so I actually proved it 2010. This is 2006, then I claimed the anticyclotomic main conjecture. So I had to prove that at some point that is mu is 0. And that I proved, that I use this, but I don't explain this mu 0 proof because it's this analysis paper, 2010, 91 pages. And I finished in a composition paper later, 30 pages. And I don't think I like to explain something of 120 pages things. And actually, so this is a black box, mu invariant to 0. But this mu invariant to 0 is the correct thing. Okay, so this is the first things I do. Then, second things I want to do is that I try to then prove that H divide HMF LP minus. This is the second thing. This is I give a proof, I will give a proof in the second lecture, but I start preparation for the proof today. So the preparation for it and to removing this is the main point of what I will do today. Okay? So this, I just use it. So I start, and second things I want to comment is that Jack Stoke lives in the 20th century, and beginning of 21st century, there's a sort of theory called the Hida theory, and notation in this theory, I totally changed at the beginning of 2000. The main point is that by the time Brecius and Rogowski attached to motive to Hilbert modular Hecke eigenforms using the unitary group. Inside the unitary group, Shimura variety, it is Grothendieck motive, but you don't know the data conjecture for this kind of motive. So therefore, for Hilbert modular, it is just you have a motive giving the same L function. And so I decided to call Hodge type of the motive. So you have a F Hilbert modular form, Hecke eigenform, and you have a motive, and then you have a Hodge type kappa. So that is kappa 1, kappa 2, because Hodge type is over complex numbers. So kappa I is the sum of kappa I sigma. Sigma runs over the place of IF, all embedding of F, right? For each place you have a Hodge type. And this, I decided to use this to be a weight of the modular form. And everything after that I wrote uses this Hodge type. And it is also Hodge-Tate type of Galois representation attached to rho f. And for example, number theories has some sort of choice often makes, and the Iwasawa usually use from the tradition of Kumar, that Iwasawa uses arithmetic Frobenius. On the other hand, so Andrew Weiss followed Iwasawa all the time. He used arithmetic Frobenius. On the other hand, Richard Taylor, he wants to do algebrogeometric proofs often using for Shimura varieties. Then, of course, he needs to follow Grothendieck to use geometric Frobenius. Then the Hodge type and so on sort of reversed. I'm in between. I don't so much care. Sometimes use arithmetic Frobenius if I like it, and sometimes geometric. So sometimes the order of this, either one is bigger and either one is less, kind of things could be reversed, depending on the situation. Okay, so in a setting, so the Jack used the classical sort of weight. That is, in my correspondence is K, the weight K for Jack is K1 minus K2 plus I. I just write I for IA. And sometimes this is identified with sigma in I of sigma, all component, parallel weight 1. So that means kappa 1 is bigger than kappa 2. Okay? And then W is what? The W is, I think, kappa 2. Kappa 1, I'm sorry. Kappa 1. This is something I use hereafter. So all the papers after this 2003 Springer book, I use this kappa notation. All right? And as I said already, so you have a totally real field F over Q, and this is P unramified. And perhaps I said that P is bigger than 5. 2 and 3 bad. First of all, most of you agree that 2 is the king of prime, so you can't treat the guy. And 3 is wrong because even P unramified in F, the Hilbert modular variety has an elliptic point of order 3. That in the case of elliptic modular, the singularity is nothing so much serious, but singularity in this elliptic point of order 3 really affects them. But if P is bigger than 1, you can pretend that your congruent subgroup is neat, in the sense that you just go up a little bit of smaller congruent subgroup of index prime to P, then you kill this 3 thing. So everything works better for P5. And that's the main reason you need this kind of assumption. And you will see this assumption basically everywhere. The Jacques talk is perhaps okay, even 2, right? Almost okay, I think. But anyway, 3 is okay, certainly. And so this is that. And then you have infinity. So this is a maximal multiple ZP extension. Then you have an anticyclotomic guy, and you have a cyclotomic guy. And this is isomorphic to ZP to the degree of F. Oh, this is F. I forgot to put M here. This is M. This is a totally real field. This is CM field. And P totally split. I mean, you have a PCM, periodic CM type. I think Jack wrote capital P or something. But anyway, P splits here. Any prime above Roman P splits here. So it is unamplified up to actually M. And this gamma group, I write gamma plus M. This guy, I write gamma minus M because Jack uses this kind of W plus or W minus, something like that. But I go back to Iwasawa's notation. And so this one is gamma M. And of course, this is isomorphic to gamma F plus. You just descent quadratic restriction P is bigger than 5, so that's fine. Bigger than 3, so that's fine. And that's the essential notation. And one more thing, perhaps I recall that Jack defined H nearly ordinary. So the nearly ordinary Hecke algebra of level capital N. N is the Artin conductor of induced representation of that psi to F. And this one I call just H. It looks like Hida no, and no good. And this is a stupid joke. Then he specialized it at finite weight. Perhaps he wrote something like that. So I call this H capital P. What P is? So I have a spectrum of, so Jack introduced in his lecture W node, and I think it was W node, and O double bracket W node, the lambda node, perhaps he wrote. And this is a Iwasawa algebra for H. And this guy, I totally, because my base ring is W, so it's confusing. So therefore, I just write this guy to be gamma bold face. And so this is a prime of this gamma bold face. Gamma bold face is almost OP cross times OP cross divided by O cross. Well, here O cross is O is an integer ring of. In Jack's talk, it was something like my W, the width vector ring of finite extension. I don't extend finite because I assume that my character chi, anticyclotomic chi, has order prime to P. And this one also. If you can lift chi like that, then you apply, take modulo P and then Taihimura lift back, then you can all the time assume this guy is also modulo prime to order prime to P. And that's kind of easy. And so for the value, these characters have values in this ring, discrete valuation ring W. Okay. Therefore, if you have a pick X and Y, the pair, the character corresponding to this is X to the kappa 1, Y to the kappa 2. So this is a character having values in cost W. And this gives rise to a prime ideal, this one, plus some information of Neven character you need. That I sort of ignore, but of course there is. And this gives a algebra homomorphism from this lambda node to W, and this is its kernel. This HP is H modulo PH. So H itself, as I perhaps commented in the Jack's lecture, that it is actually free of finite rank. over Iwasawa algebra, lambda naught. And because of that, this is exactly yes, the exact control theorem we call. And so that also I need this kind of assumption. And all right, then I consider the Taylor to be induced representation from M to F of this psi, and rho bar to be this one, rho modulo maximal ideal. So it is induced from M to F, psi bar is the psi modulo maximal ideal. And this level n outside P is a prime to P part of Artin conductor of this guy or that guy. So then this H can be split into two pieces, T and a complement, T. This is a local ring corresponding to this rho or rho bar. In other words, you have a Galois representation rho T from Galois group over F into GL2 of rho T in the good cases. And you reduce modulo P, you get this guy back. It's a deformation of rho bar to this rho pi. So this is a local ring giving rise to it. To this guy, to have that, to have this rho T and to have this T to be universal, I need to assume some condition. This is also perhaps Jack mentioned that A1 is that this one is not so important, but chi as order prime to P that I already mentioned. And with prime to P conductor, the prime to P part of the conductor made of split primes. Primes split for M over N. This condition you can totally actually avoid, but that becomes technical, so I just make it this way. A2 is an important condition that local character chi Gothic P. So you have a CM type, Jack fix. Then this gives rise to periodic CM type. Perhaps Jack wrote this as a capital P or something like that. So this is made of several primes, P1, PR, or something like that. And this chi pi, you have chi, you restrict it to decomposition group of chi pi, and that is non-trivial. So this is so-called P-distinguished condition. And this is necessary to have a universal deformation ring attached to this border face T, or the existence of universal deformation ring of rho bar, I should say, nearly ordinary deformation ring. And often R equal T theorem. This is proven by Fujiwara, generalizing Taylor-Wiles method to Hilbert modular case. His paper in our archive. Wiles regretted that he rejected his paper to others. Fujiwara is so proud of himself, he never submitted anywhere. And proof is correct. And also it is explained in my Oxford book. (2006). And A3, it often happens to of this RT theorem things, that it is high restricted Galois group. So I just write Galois, base field of Galois group, as Jack mentioned, the square root of minus 1/2 of P minus 1P, whereas P star is non-trivial. That implies this guy is irreducible over that field, and that Taylor-Wiles and also Fujiwara use. Nowadays, perhaps many cases of this condition removed by a lot of people, Jackson and Shekhar kind of, Chandrasekhar Kale kind of people, but I didn't check everything. I don't care about such kind of rather small improvement. Anyway, so this A2 and A3 are basically necessary. A1 you can remove, and how to remove, perhaps I can explain it. And so let's start. Okay, so how you remove the 1 over P. Okay? And so the Jack perhaps proved this H over the ranking product, since I just write it ranking, Jack wrote 5 of psi or something like that. I need 5 of psi or both later. So I just write this is a ranking product. And this is equal to Katz's periodical function. He wrote L1, L2, so L1, L2, and some junk factor there, but I forget about that. And then HMF L minus P. This is the equality he sort of explained. And L1 is basically the Katz's periodic, so L1, so it's a 2 variable actually. PQ is now in spectrum of lambda. Lambda is W double bracket gamma. Okay, so this is your submodule. And so it's a W point, for example. Then you get, so this comes from family of psi, branch character psi family. And this, Jack chose some other character phi. And then this value is Katz's periodic L evaluated, say, branch character. This branch character is psi inverse phi, and evaluated, so things goes something like that. You have a universal character psi of the Galois group of M into this lambda cross, that the gamma, the Jack wrote G infinity C or something, but this is a class group of M of conductor C, P to the infinity kind of things. And he split it into finite guy and gamma M, right? And the branch character means character of this guy, and this guy is this psi inverse phi. And the universal character phi corresponding to psi is that this gamma delta and gamma, delta is here, no, delta is here, gamma is here, is just a psi gamma. It is inverse, so actually psi delta inverse, and gamma itself inside this Galois group gamma M. That's a universal character. Okay? Then this universal character, big psi modulo this kind of P, I just write psi capital P. And the same way for phi, so it is psi P inverse. Oh, so therefore I don't need to take inverse here then, because I put the inverse here. Right? And phi Q something like that. L2 PQ is slightly different. Perhaps Jack didn't explain, but psi P inverse IQ complex conjugate in inner conjugate, something like that. Okay, so what I need to prove is that if mu invariant of this kind of L, this cat periodical itself is 0, then mu is L1 is 0, and mu of L2 is 0. So P doesn't divide this guy, and therefore this denominator P, just a Roman P, should show up H. And therefore that remove the this 1 over P. That's how things go. So I need to prove one of mu, vanishing of mu, as I said. So I did two things, a little bit of explanation. 2010 annals paper. This, I actually got an idea in about the year 2000 for this stuff. And I actually gave a lecture in Taiwan, Hsinchu, TI, ICTS, TIS, or something like that, Taiwan version of this guy, this kind of institute. And nowadays it is in Taipei, but at that time it was Hsinchu. And then Chin Chai comes to me. He said, your proof won't work. So I worked with Chin after 10 years, and I proved 2010 this vanishing of mu. And this proves that as long as the split conductor condition, so that I perhaps name it A1, A2. So this prime to P part of this is just I call split conductor assumption S condition. As long as S satisfied and M over F ramifies somewhere, in finite places, then mu vanishes. Mu, 0. So this is 2010 announced paper. Not just mu, actually, mu of this cat periodic curve, you restrict it to gamma minus m. Whatever branch, okay, but I restrict it to the gamma minus m. This restriction, mu vanishes. That, of course, implies mu of L vanishes. So this is a very strong result. However, I need to assume that M is not in the Hilbert class field. And this is a sort of two things. You expand this Iwasawa power series. Jack wrote it as a summation over Eisenstein series indexed by ideal classes of, say, M. Maybe actually, strictly speaking, this way of writing is not too good. So it's CRM, at least this CP, indexed by this one, actually. And then it becomes gamma thing, each piece. Then this partial object has Iwasawa expansion, power series expansion. On the other hand, Eisenstein series has a Thayer-Tate expansion. I proved that these two expansions, each is the same. However, variable depends on this index set. And so the Thayer-Tate expansion is just over GM tensor O. formal comparison. This has a FQ variable. Finding with FQ variable power series ring over W. And that variable T depends on the choice of index, the classes. And actually, I proved that for starting from multiplicative variable GM, and then if this is index, this is a representative set AI, then you can find some sort of element AI in OP cross such that, because this is GM and tensor O, you can raise power to the AI. And this is the dependence on this AI. So it's basically Eisenstein series expanded by TAI, and it's linear combination of that. So this AI is actually, operation of this AI is transcendental, I proved. So this EI of each guy is algebraically independent over all work of FP bar. It's a reduction modulo of P because I only care mu invariant of this affine ring of GM at tensor O. That's one thing. That basically proves the, I identified this expansion basically Iwasawa's expansion, and it is algebraically independent. Now there's a one variable T, I know the relation, and therefore mu vanishes. That's how things go. But it is a heavy arithmetic geometry, modulo P, so it's Chinli's contribution is quite large. Anyway, then I just, but independent doesn't necessarily mean, I mean, to show this is non-zero, first I computed by Q expansion principle, Q expansion of this guy. And then I proved that. So I can actually, this I can do the FP bar, but I can also do W over P to the MW if I want. Therefore, I can actually compute exact mu invariant even the everywhere and ramified case. And that's the result of this analysis paper. The composition paper, one thing I missed when I wrote this. So I computed, perhaps everybody saw this, I guess, erasing. I computed, therefore, this gamma minus P, gamma minus M, this is the P to the FQ. And Iwasawa power says, therefore, has F number of variables FQ. And Hilbert modular variety has this dimension, and therefore Seatate coordinate has number of variables the same. And that's the key reason that this works. And therefore, I can only treat restriction to minus component. However, I missed that you have gamma M is actually gamma M plus and gamma M minus. So the Iwasawa algebra, lambda is lambda plus guy and tensor lambda minus guy, right? So I pick a point P here, and then I move the variable here. In other words, I consider the invariant P times gamma minus M. So you restrict the cat measure to P times gamma minus M. I can still compute basically the mu invariant on this. And actually what I proved is that you move around P of inf mu of this L restricted P times L gamma minus M is actually inf is 0 without any condition, one condition of S splitting condition necessary, but Therefore, mu invariant is all the time 0 if you consider cat periodic graph. And this L1, L2 contains all the variables. So above mu invariant 0, so I won. And this is how things goes. Okay, so that's the kind of sketch of the proof of this mu invariant thing. And so I now start preparation for the reverse divisibility. So if this really you can prove, reverse divisibility means what? HMF L minus Jack's direction is this divide H. And this H is by R equal T theorem is HMF Iwasawa power series corresponding. I just write F because capital Roman F is base field. And this Jack explained in his talk that if you have a surjection, then you have a divisibility this way. If it is equal, they are the same. So the equality is known under this assumption A2, A3. So I need to prove actually H divide HMF L minus. This is equivalent. So I pick some P now in spectrum of lambda W. Yeah? This is a power series. So you evaluate at P, or evaluation at P just means H mod P. It is prime idea. So I want to show this divide H MF. This is a constant, it doesn't affect L minus P for some good point P. So I have P here. Right, this is a Nakayama's lemma, right? So we know this. So HMF L minus P, I got P here, times something power series is equal to H. U is in lambda. Then you reduce it modulo capital P. If you can prove actually HP divide HM over F, LP minus P, if you can prove this, it implies UP is a unit. And lambda over P lambda is W. And Nakayama's lemma tells you that U is a unit in loss. So you win. So I need to find a good point, P. And a reduction argument, I do. Yeah? All right, so I at least I said I equal T theorem, I quoted a lot. And if you saw, most of you at least see, look at that, the Wiles 150-page paper of Fermat's Last theorem. Huh? And he imposed a lot of complicated conditions at each prime ramifying in the Galois representation outside the auxiliary sort of conditions. And there's a good way of not to state that sort of way. And the point here is that So a little bit of deformation theory. So in Fujiwara's case, it's much more awful, obviously. And in this kind of setting, it's a very easy way to formulate. So that I take, so whatever Galois representation question of some Galois group over field K you have, then I just write K question mark to be the splitting field of question. In other words, this is K bar kernel of question. So for the base Galois group, what I take is that F rho bar. Then over that, I take F P rho bar. It is maximal P profinite. Only P ramified extension. So this Galois group is just an image of over. Okay. So if you are prime, here you have some prime Q or something. And if it is outside the P, ramification concentrated on this part. And if you look at carefully Weil's condition of ordinary case for this kind of induced representation, it just means that the inertia factor through this quotient. At P, you have real thing. And therefore, Weil's deformation all the time factor through Galois group of this, I call it just G. This kind of stupid maneuver, for example, my 2022 book of elementary modular Iwasawa theory, it's a world scientific. I explain in chapter, I think 8 or something. At least F is Q, and argument is the same. And okay, so it is just, I said, R is universal, means that you have a Galois representation rho R of G into GL to R, such that rho R of that for Q dividing the level, but prime to P, then because it is induced representation under MF of psi bar, something like that. And this restricted at DQ, big Q. So I have the splitting condition S. So this Q equal big Q complex conjugate. So this is just a psi bar complex conjugate inside, right? So this forces that rho R modulo rho R restricted because it factors through this triangular form. So the dq is epsilon q delta q 0 star. This is Weil's condition he explained. And if this is the case, then it's basically the deformation condition tells you that it factors through. If P at P, so Gothic P, then this rho R, or any deformation, is epsilon P delta P 0 star. And I forgot the condition delta Q is congruent to psi C mod maximal idea of R. This is delta P congruent to psi C modulo maximal. And this is the condition of virus. This I have to impose. It's not automatic because ramification goes over everywhere above. And so that gives you this ring R. And R equal T theorem is that R is isomorphic to T, and rho R is brought to rho T. Okay? And so hereafter, I forget about R, and I only work with T, but they are same thing. Okay. Then I still have a lot of time. I have this H, and I decompose it to C and T pop. So you take H modulo P. So this is H over PH. So this is a T, the same thing, TP direct sum P pop P. And this is exactly the modulo P map. This is exact control theorem. In other words, this is P modulo PT. So this is a universal. This bold-face T is universal in this sense. And what is this universality for this modulo P? It's basically the information of capital P gives rise to, because Iwasawa algebra structure of lambda 0 is basically made out of these characters. So the P is a kernel of algebra homomorphism from, or the kernel of algebra homomorphism from lambda 0 to W. And that therefore it is induced from, you take modulo P, you get corresponding object epsilon P delta, delta P delta, 0 something. I don't care this. This is not controlled by lambda. I also, not delta, I mean, goes Q. Here I allow Q to be prime factor of N and P. Maybe N and sigma. It's a better choice. So you impose that the formation matches to these two characters. So therefore, determinant also match to the product. And so then that's the deformation problem of T indexed capital P. Understandable? Okay. So each guy has sort of universal property like that. Okay, so I basically repeat the reduction process of so number 0 thing is that what Jack proved, that 8MF, and I sort of augmented that L minus P divide H in lambda. So I have written that H is equal HMF LP minus times U with some U in lambda, not zero. Okay? Then the second step is that by R equal P theorem, is view that H equal HMF L minus P. No, not L minus P. F. Rasawa power series. Third point is about by Nakayama. So third point is now our target. What I do, H P divide HMF L minus P, capital P. In other words, UP is in W cross, and then by Nakayama's lemma. Oh, by the way, this is famous story. Nakayama's lemma is not proved by Nakayama, and it is proved by Azumaya and Kurl. So it is called NAK. It's not the three letter of Nakayama's name. But somehow it is called Nakayama's lemma. Perhaps he used mostly this. And Azumaya, okay. Perhaps you don't know, neither of them. I've never met these three people. But Azumaya was a professor at University of Indiana. Nakayama is in Japan. And Kurl, you know, at least a name. You. So this is the main point. So what is this P? So what is KW or kappa corresponding to this P? And of course, easiest choice is weight 2. So this K is 2, and with some Neben character. And K2 means kappa is I0. The Hodge type is 1, 0. Those of abelian varieties, weight 2. And this case, obviously perhaps the easiest, I thought. But later I actually proved in NP is okay. But anyway, it's more technical. So Jack gave a rather sophisticated definition of congruence power series. And when I was senior year of undergraduate time, I concocted this congruence number. And the definition is not at all sophisticated. And that definition is far more useful of the refined definition. And the stupid definition is far better. And because I was stupid at that time. Okay, so the point here, so this HP is therefore Heck algebra of S kappa. Kappa is therefore I naught of level N. N is the arting conductor, norm MF. Say C and a discriminant MS with appropriate Neben character. Neben character is a technical thing, and I don't explain that, but it's not a usual Neben type. If your character psi ramifies at some prime factor Q of cosec C and Q complex conjugate, two ramification, complex conjugate and original, then it is not a single Neben character. Yeah? So that to explain things is a little more complicated, so I just write the epsilon. And coefficients in W. This means that Q expansion has coefficient in W. So it's a usual Q expansion rationality I use. It comes from coherent cohomology corresponding to Hodge bundle of Hilbert modular variety. But I will explain this slightly more perhaps later. And so this is, then why not I just embed W inside C. Then I don't need to do that. If I don't do that, that just means W intersected Q bar or something. And then it is embedded in C and also UP bar. And I first have a periodic W things to descend here and then ascend there by tensor product. But it's stupid if I do this. I don't need to do that. But if you don't like this type of isomorphism, you'd better do twice tensor product. Then you pick any, so this for simplicity, I just write SW. Or more generally, SA, or any subring of complex number, I just write SI node and epsilon A. This is just a simplified notation. And this is only well defined when A contains the values of epsilon. Otherwise, Neben types is not well defined. So just pick something in SW. And I have a theta series coming from family. That means theta of psi specialized at P. This is in it, by definition. This is a Heck eigenform. And basically, by assumption A2, A3, all member, this is made of, spanned by new forms. And therefore, it's quite simple that if you write F to be this theta, CF times theta, and orthogonal complement, those belonging to other eigenvalues. Then the CF is where this is CF. CF is a numerator and denominator, and N and D inside W. And D is, of course, not zero, both nodes can be zero if this is concentric. Okay? Then I consider ideal of W, Xi in W. Xi in W, such that Xi CF in W for all F in SW. So it is generated by this denominator. This is a discrete valuation ring, so you can write this way, reduced fraction. And this is generated by H over P. It's a principal ideal because this is W is a discrete valuation. And this is the definition of HP. And I think it's far better than Jack's complicated definition. But Jack's definition, of course, good. It is very abstract and can relate it to the first congruence module. This is zeroth congruence module. So zeroth congruence module is, or this theta is W modulo HP. And Jack defined C1 using sort of Taylor differentials of PP, right? And this C1 directly related to Selmer group or Iwasawa power series evaluated at P, right? Character fitting ideal, this is generated by this guy. And if, because RT theorem tells you that PP or R are local complete intersection, then the fitting ideal of 2 is equal Tate theorem. And that's why Jack's definition is quite good. If you do sophisticated deformation theory or something like that, if we want to just prove reverse divisibility kind of things, these stupid things is sometimes better. And of course, this is kind of exercise why this is the case out of Jack's definition. You prove it. Okay. All right. Then I have a Peterson inner product. And you compute it by Peterson inner product. Then CF is what? Obviously, it's a theta self-product divided by theta f, right? And Jack explained in his lecture the similar formula that theta is after I divide this omega, the long period, twice I is equal to HMF LP minus at P slightly, usually Shimura doesn't care integrality. He usually care only algebraicity or rationality. And he usually want to make things general as far as he can. Therefore, his formula when he proved could have a junk factor. I cleaned it up, and that perhaps best formula is my IMRN paper 2009. Of course, I used this kind of things in my 1981 paper, congruence of transform paper. But yeah. So this you can write, of course, omega 2. You can write this way. And then this is a denominator, and the guy is a numerator. And you multiply this guy to this. Then, by definition of this guy, if this guy multiplied, you get something integral. As long as if this is integral. If is in W, then H M over F L minus P. You multiply this guy to CF, you get integer. That means it is divisible by HP. This is what I want, right? So what I need to prove is that, so further for simplicity, I just write this to be S. SW is S. So what I need to prove because this you require for all F. Huh? So the all F, not just single F. Any questions? Okay, so what I need to show the set theta with this set as space of modular form, I is in W. So this is a question. How you can do that? And idea is that you remember Eisenstein series considered to be a geometric sort of modular form, evaluated abelian variety at complex multiplication. A is an ideal of some order of M, is basically partial function of LA of like 0 or 1, depending what choice you make, of some Hecke character phi E kind of thing that Jack explained, right? This means by Katz theory of geometric modular form that actually strictly speaking divided by omega to the something, but for this weight it is y. And by Katz theory, this is in W. You remember? W is W intersected Q bar. Not just a completed object, but an algebraic generalization. So I need to show that something not the L value theta of F omega to I is in W. So I need to find out that this is some Hilbert modular form with integral Fourier coefficients of XA. Actually, another one is two variable things. Whether this kind of Hilbert modular form on GL2 twice with this property. You give yourself data of theta and F, and somehow you concoct something like that. Then you win. And there's so-called Shimura series, not Eisenstein series. I will give a definition perhaps next lecture. Shimura series, I call. This is 1981 announced paper. Schumann's paper is not at all easy to read. However, he doesn't make error. In his red book, there's only one error, and you should find it out. No typo. It's not typo. Serious error is only one. And most of his paper doesn't have error. And difficult to read, but you can rely on it. My paper, difficult to read, don't believe it. And it is basically made of two ingredients. This theta, this can be any, actually, how you can say, I would say phi, say higher weight modular form. Okay? And higher weight, but it has to be this type, this theta series, a CM form. And you have, so in this case, weight is 2, K is 2. Two lower weight form. Say F is used, so I have G and H. So in this case, there's no two lower, means that weight is just a weight of this guy is 1, and this guy has to be 1. But if you start from higher weight, you get much more choices. And this one is actually has to be theta series of weight 1. Out of that, he concocted HZWS. This is the series. That you get you plug in Tian point, so it's something from XA, because it doesn't work with Katz's notation. He hates Katz. And therefore, he plugs in CM point in his cell. But that corresponds to Katz CM abelian variety. Yeah? And W node, and S, you do. Then you get a ranking product of big theta tensor, basically product of Z theta 1. Ranking product itself can be defined non-Hecke eigenform, and this can be non-Hecke eigenform. Evaluated basically at some S naught. S naught and S is related. And I still have time, right? 11:15, okay, 10 minutes. This ranking product has a pole, and I normalize ranking product to has pole at S is, I think 1, but at any point is okay. And this is basically Peterson inner product. And this one has a pole corresponding as pole, and you take a residue, the psi is a residue of this H at appropriate point S. I think S is 0. But anyway, that gives this. Therefore, you divide it by omega 2R. Okay? Therefore, I need to write down this I will explain that as I said, Shimura created this. Perhaps you remember dependent lecture or the Ben Howard lecture or something, that you consider M2F and determinant as a quadratic form. And then its similitude group is GR2 times just you make a fiber product with determinant GR2. This is signature 2, 2. And it's basically Hilbert modular form twice. And similar result of this kind is any GO2n, those orthogonal group has signature 2n, or UMN, or GU perhaps. And that makes his paper so hard to read. Secondly, he computed Q expansion or Fourier expansion, but he just wanted to treat everything at one time, and therefore, the integrality he doesn't care, or rationality only. And even rationality is quite hard to do this kind of big group. But that's for him, it's basically nothing. And it's a very special case of this. And I computed the Q expansion of this guy absolutely. And so I can apply this cat theory. And I don't hate cats. I don't hate Shimura either. But that's how I prove this. Therefore, at least for this integrality of this ratio of Peterson inner product from starting integral object. Okay, so I need to now show S is SW, and this is bound by theta phi and theta phi prime. This now I use M and the norm MF quadratic space, and that produces theta series. You choose nice Schwarz-Brunner function and to arrange the weight. Schwarz function gives you a weight, Brunner function gives you a level, and spanned by this over W. That I try to prove. This is both, of course, weight 1 and 1 thing. And then apply this. That's how I prove. But it's hard to do to show this. The product is actually essentially 4 variable theta series phi tensor phi prime. In other words, I now use Quaternion algebra over F everywhere and ramified at finite place. And definite, totally definite. This imposes me to be FQ even. So I prove this kind of result for even degree field. So for odd degree F, I make a base change and descent. I prove everything over even degree field and do quadratic base change again. And that's how, so thereafter I assume FQ as an even degree. Okay? Then I use now the, that this B decomposed in M direct sum M. And so the 4 variable theta series, so B reduced norm is a quadratic space over F of dimension 4. And you can decompose it because it's everywhere unramified. M can be embedded into B. And M tensor Fm is M direct sum M. And this acts on M by this embedding, say, iota. Maybe it's a rho, I would say. A tensor B of this element B to be rho A, B rho B complex conjugate or something. And then this splitting gives this type of splitting. And therefore, first, I prove that this S is spanned by integral theta series for variable. So I try to prove that this S is spanned by theta of 4 variable coming from En. This simulus theta series is made out of quadratic space of totally indefinite guy. I now shift it totally definite guy everywhere I love. Okay? Then how you can do that? So I use Jacques-Lagrange correspondence. And I could solve this kind of problem to span space of cusp forms by 4 variable definite quadratic form called I-class basis problem. This is a precursor of Jacques-Lagrange correspondence. And so I normalize Jacques-Lagrange correspondence a la I-class. But I could all the time do it rationally. I do it integrally. Okay, space for automorphic form. So Jack perhaps explained SI0 and epsilon W kind of things. I wrote SW, and that is S. Corresponding guy is SB. That is SB of A. You take any ring. This is just a function of B cross over B idealized cross. To A such that, so F I call F B U is epsilon U F B like that. U is in Yamaha node N. You see, B is everywhere unramified. So BA, finite are there, is isomorphic to M2 FA, finite are there. So I identify it. Then I have a GL2 FA, finite are there. BA, infinity cross is equal. You have a gamma hat node N, open compact gamma 0 type, gamma hat node N also living here, therefore. And I consider this space. And I still have time. Almost run out of time. So as usual, as a stupid lecturer, I beg you to extend my lecture 5 minutes. If somebody objects, I go away. No. Okay. So one thing is that therefore I can consider also delta hat. Something alpha M2 or hat. O is integer ring over N. N part of alpha is ON, N times ON, N localization, ON cross, and determinant X is FA finite cross, something like that. This lives in BA finite and also lives in M2. FA finite. Okay. Then this gamma hat, delta hat, is a disjoint unions of Tn and runs in integral ideal. This is Hecke operator. Those having determinant generating the ideal, integral ideal n. And for example, for FSBA, you apply FTN, you decompose Tn is disjoint union of alpha gamma nodes hat n, then this is supposed to be some alpha, this alpha of epsilon alpha inverse. If the epsilon event types is concentrated on this case, I assume that is the case. If otherwise, I need to put it something also here, and that makes things complicated. F x alpha, something like that. Then in my formulation of Jacques-Lagrange correspondence, totally different from what Dippendorf did. So in the same way, the Hecke operator acts on also S, right? So JL theorem is that there exists an isomorphism JL from S. I think I put above. Oh, this is below. It doesn't matter, but I will continue to make error. So SB, B, S, C, this is M2F side. This is B side. Such that JL applied Tn and the cotangent side is Tn applied JL side. Okay. I think I spent 4 minutes and perhaps I stop here. I will start next time explaining why this implies that actually the theta series of 4 variable generates even over W of the W integral forms. I do it next time at the beginning. Okay, thank you.
Thank you very much. Are there questions or comments?
Sure, this map is not unique. You have JL, you multiply, say, 3, it still works. Or you multiply anything commuting all Tn, both sides, it's still satisfied. So it's non-canonical because Dippendorf proved, explained that as a correspondence of isomorphism plus automorphic representation. And each automorphic representation has ambiguity of scalar because it's absolutely reducible. So now I need to rigidify it.
Any other question? No. Then let's thank the speaker again.
Yes.